Now we will take a look at the Weiss theory of ferrimagnetism. As we introduced in the previous video, the ferrimagnetic sublattices, A and B sublattices, have opposite magnetization, but they don't exactly cancel out. So in Weiss theory, we need to consider the interactions between AB, AA, and BB sublattices. Okay, so A and B sublattices are not structurally identical, so A and B can be different atomic species or same ion in different symmetry locations. So we're talking about symmetry locations in the crystal. So we have to consider A sublattice, B sublattice interactions, A sublattice interactions, and B sublattice interactions. Now let's think about how we can take into account these interactions. The first thing we need to note is that A-B interaction is antiferromagnetic. On the other hand, AA interaction is ferromagnetic, and similarly BB interaction is ferromagnetic. Now I call N the total number of ions per volume. I call alpha the fraction of A ions. So it's the number of A ions divided by total number of ions. And I call beta the fraction of B ions, number of B ions divided by total number of ions. So with that, if you look at N times alpha, you will have the number of A ions per volume. If you multiply N with beta, then you have number of B ions per volume. And because alpha is the fraction of A ions and we only have A and B ions, we have beta is equal to 1 minus alpha. I call mu sub A average magnetic moment of an A ion. And mu sub B is average magnetic moment of a B ion. So with that, if you want to write the magnetization of the A sublattice, you have a number of A ions per volume N, and per ion we have the magnetic moment mu sub A, and the magnetization of the B sublattice will be beta N mu B, and the total magnetization M will be MA plus MB which is alpha n mu A plus beta n mu B. Okay, so now that we know the magnetization of the A sublattice, B sublattice, and total magnetization, so MA is alpha n mu A, MB is beta n mu B, and total magnetization is alpha n mu A plus beta n mu B. We can write the Weiss molecular field acting on the A sublattice. So Weiss molecular field acting on the A sublattice due to the antiferromagnetic interaction with B sublattice is minus gamma AB MB, and ferromagnetic interaction with the A sublattice plus gamma AA MA, and Weiss molecular field acting on the B sublattice is minus gamma AB MA and plus gamma BB MB. So we have antiferromagnetic and ferromagnetic interactions included. Okay, now we're going to look at what happens for temperatures greater than Tc. So let's take a look at temperatures greater than Tc. Well, we have the usual Keri law. The susceptibility is magnetization divided by the total field acting on the material. This is C divided by T, that is Keri law. If we are able to write the total field acting on the magnetization, and magnetization is C times H total divided by T. So we can write for A sublattice magnetization, C times the total field is the applied field H plus the Weiss molecular field acting on the A sublattice divided by T, and magnetization of the B sublattice is C times H applied field Weiss molecular field acting on the B sublattice divided by the temperature T. So we have these two results, and now let's summarize what we have here. So we can use the following equations. M sub A is equal to alpha n mu A, the number of A ions per volume times magnetic moment per A ion. Magnetization of the B sublattice is beta n mu B, and I call these equations 1 and 2. The total magnetization M is equal to n alpha mu A plus beta mu B, and this I call equation number 3. Weiss molecular field acting on the A sublattice is minus gamma AB times MA, which is MB, which is beta n mu B, plus gamma AA MA, which is alpha n mu A. I call this equation number 4. Weiss molecular field acting on the B sublattice is minus gamma AB MA, which is alpha n mu A, plus gamma BB MB, which is beta n mu B. This is equation number 5. And we have MA is equal to CH plus HWA divided by T. So we have alpha n mu A equals to CH plus HWA divided by T, and we have also beta n mu B equals to, using Keri's law, C H plus HW B divided by T. And so this is equation 6, equation 7. So using these equations and eliminating, if we eliminate from these equations mu A, mu B, Weiss molecular field A, Weiss molecular field B, to solve for total magnetization divided by H, the applied field. So H is applied field. This gives, for 1 over the susceptibility, H over M, which is 1 over chi, the following result: T plus C divided by chi 0 divided by C minus B divided by T minus theta. So this is the end result for the susceptibility of the ferrimagnet. And at high temperatures, you can see that the behavior is chi C over T plus C over chi 0, which is Curie-Weiss law. So on the other hand, if you look at when is chi infinite, or 1 over chi is equal to 0, that's the phase transition point. T plus C over chi 0 divided by C is B over T minus theta, and we find that T plus C over chi 0 T minus theta is equal to BC, and this has a solution at T is equal to theta P, which is called the paramagnetic Curie point. Okay, so if we plot 1 over chi as a function of temperature, experimentally we find a different Curie point. That's the ferromagnetic Curie point. So this is our paramagnetic Curie point. Experimentally, we find a slightly different Curie point. That's the ferromagnetic Curie point. So experimentally, the 0 point, theta F, which is called the ferromagnetic Curie point, this differs from the paramagnetic Curie point a little bit, and the reason we can give as a remark here is that theta F differs from theta P because even above Tc there is a short range magnetic order. and this order is maintained for a few degrees above Tc. The material is not homogeneous. We don't have the same coupling strength at all locations, so this basically the true paramagnetic Keri point is a little bit higher than the ferromagnetic Keri point. So this is what we see for T greater than Tc. For T less than Tc, we have the magnetization given as the difference between the absolute values of Ma and Mb, where the Ma magnetization is given by Langevin formalism and Ma Brillouin function, which is coupled with the Weiss molecular field, Ma Weiss molecular field acting on A divided by Boltzmann constant times temperature, and the B sublattice magnetization and Mb Brillouin function, Mb Weiss molecular field acting on B divided by kBt, so that's the quantum version. So we can find Ma is equal to n magnetic moment per A ion, a Brillouin function, Ma gamma AA Ma minus gamma AB Mb divided by kBt, and at the same time we have Mb is equal to n number of ions per volume, magnetic moment per B ion, Brillouin function evaluated at Mb gamma BB Mb minus gamma AB Ma divided by kBt. So these are two dependent equations, must be solved numerically. Okay, so these two equations should be solved numerically, and when we solve these equations, we find the magnetization as a function of temperature for the A sublattice. We have a certain magnetization versus temperature. For the B sublattice, we have a certain magnetization versus temperature. So a typical one will consist of the contribution from the two. So this is basically the magnetization M as a function of temperature. So this is Ma, this is Mb. So depending on how exactly these magnetizations, sublattice magnetizations, change with temperature, we can have the M versus T curves differing a little bit. So we have a remark here. So we need to have both sublattices. This is for the case where I have both sublattices have the same Tc. And another remark, so since we have M that depends on both the A sublattice magnetization and the B sublattice magnetization, factors like distribution of ions, molecular field constants, M may not vary monotonically with temperature. Okay, so we may find that, as an example, here is the A sublattice magnetization, here is the B sublattice magnetization, and what happens is that MA, so the total magnetization decreases and it becomes 0 first, and then it becomes 0 again. So we may find that at some point here, these two are equal, although on this figure they don't seem to be equal, but let's assume that they're equal. And we have two 0 points in the magnetization, and this point where I have the first 0 is called compensation temperature. So at a certain temperature, the A and B sublattice exactly cancel each other, and there it behaves like an antiferromagnet. So A, B magnetizations cancel each other at the compensation temperature. And we can find that even more complex behaviors can be observed. That is more than one compensation point is possible when you have three sublattices, A, B, and C. So in that case, we would find that there can be more than one compensation point. So the story can get a lot more complex. Okay, so to summarize, in ferrimagnets, we have to consider AB, AA, and BB interactions. Calling the number of ions per volume, A ions per volume N alpha, and B ions per volume NB, with alpha the fraction of A ions, beta the fraction of B ions, and N is the ion density, total number of ions per volume. We can write A sublattice magnetization as alpha N mu A, B as beta N mu B, and we can add them up to get total magnetization. Weiss molecular fields, we have to consider antiferromagnetic interactions with the other sublattice and ferromagnetic interactions with the same sublattice, as we can see here. And for T greater than Tc, we have Keri's law. Susceptibility is m divided by the total field, that is C divided by T, and including in the total field the applied field. So this is applied field H and Weiss molecular field. We can write the Keri's law for the two sublattices, and combining these equations we obtain 1 over chi is of the form T plus C over chi 0 divided by C minus B over T minus theta. So it can be written in this form. So C is a constant, chi 0 is a constant, B is a constant, etc. Theta is a constant. So the temperature dependence can be written in this form. If you solve these equations for m over h, and we can see that 1 over chi is equal to 0 gives us a paramagnetic Curie point, which differs slightly from the ferromagnetic Curie point due to the short range interaction that basically exists even above the ferromagnetic Curie point. So ferromagnetic Curie point is basically Tc, but for it to become a true paramagnet, we have to wait for a few more degrees. For T less than Tc, we write Langevin formalism. For alpha, which is mh over kt, in the brilliant function, we substitute the Weiss molecular fields for A and B sublattices, and we can find m versus T, and depending on exactly how A and B sublattice magnetizations change with temperature, we can have different scenarios. We can have the M increasing for a little bit and then decreasing, and we can also have a situation where the magnetizations exactly cancel out at the temperature called the compensation temperature, and including this temperature and Tc, we can have two 0 points in M versus T. Or if we have a more complex situation with three sublattices, we can also have more than one compensation point.